Today, we are taking an incredible journey, a journey deep inside the atom to tell the story of how we discovered the fundamental building blocks of, well, everything.
Now, what if I told you that you, this screen, and everything you've ever touched is 99.9% empty space? I know, that sounds completely impossible, but it is a fundamental truth that science uncovered on its quest to understand the atom. It's a journey that seriously challenges how we see the solid world all around us.
So where does this story begin? Not in a high-tech lab, but actually in ancient Greece, with a simple but incredibly powerful idea. An idea that laid the groundwork for our entire picture of matter today. For more than 2,000 years, the atom was really just a cool concept. The ancient Greek philosopher Democritus, he imagined just cutting a piece of matter in half, again and again, until you finally hit a tiny, uncuttable particle. He called it atomos. But it stayed just an idea until the early 1800s, when John Dalton came along and turned it into the foundation of modern chemistry. He gave scientists something they could actually test. Dalton's theory was, and I mean this, absolutely revolutionary. He said that every element has its own special type of atom, and these atoms combine in fixed, predictable ways. This was genius because it explained why chemical reactions are so consistent. It's why water is always H2O and never H2.50, right? It gave science its first real, testable model of the atom.
Okay, so if atoms were real, what did they actually look like? Well, the first attempts were kind of like early drafts of a masterpiece. Each one got us a little bit closer to the truth, but they were still missing some pretty crucial pieces of the puzzle.
The first big rewrite came in 1897. J.J. Thomson discovered this tiny, negatively charged particle called the electron. All of a sudden, the indivisible atom had parts. This meant the old model was officially broken, and Thomson had to come up with a new one to fit his discovery.
And what he came up with was beautifully simple. He imagined the atom as a sort of soft, solid ball of positive charge, with these negative electrons scattered throughout. Think of it like raisins in a plum pudding. It was a totally logical first step that made room for the electron, but it wasn't going to last long. Yeah, that whole plum pudding idea was about to be completely shattered. A scientist named Ernest Rutherford decided to test it. He fired these tiny, positively charged bullets at a super thin sheet of gold foil. He totally expected them to just zip right through the soft pudding. But what he found was just astonishing. Most of the particles did go straight through, just like he thought. But a tiny fraction, we're talking about 1 in 8,000, bounced almost straight back, like they'd hit a brick wall. 15-inch cannonball at a piece of tissue paper, and it came back and hit you. Something small and very solid had to be in there.
And this led to a radical, brand new picture. The atom wasn't a solid pudding at all. Nope. Almost all of its mass was packed into a tiny, dense, positively charged center, the nucleus. And the electrons? They were orbiting way, way out. This was the moment science proved that the atom, and therefore all matter, is mostly just empty space.
But Rutherford's model had a major flaw. According to the physics of the time, an orbiting electron should constantly be losing energy. This would cause it to spiral down into the nucleus, and the whole atom should collapse in a split second. But obviously atoms are stable, so something was still missing from the picture.
The solution didn't come from the normal physics of planets and cannonballs. It came from Niels Bohr, who pulled in a wild new idea from the super strange world of quantum physics to explain why atoms don't just disappear. Bohr proposed that electrons were locked into specific energy levels, or shells, kind of like planets, but in very rigid, specific orbits. They could jump between these shells, but they could never, ever spiral inwards. And this wasn't just a guess. It perfectly explained the unique patterns of light that different atoms give off, something the old model could never do. It was a huge step forward.
So Bohr's model was a huge step, but the true nature of the atom was actually even stranger than anyone could have imagined. Physics was about to take a quantum leap away from a world of certainty and into a world of pure probability.
And this is where the picture gets really weird. See, Bohr saw electrons as tiny little planets in neat, predictable orbits.
But scientists like Erwin Schrödinger and Werner Heisenberg discovered that's just not right. An electron isn't just a particle, it also behaves like a wave. And that means it doesn't have one single precise location. It exists in this blurry cloud of probability.
This brings up a massive question, right? How do you describe an electron's location if it doesn't really have one? I mean, how do you map a cloud of pure possibility?
This is the very heart of Heisenberg's famous uncertainty principle. It basically says there's a fundamental limit to what we can know about a particle. The more you nail down an electron's position, the less you can possibly know about where it's going, and the other way around. We can literally never know everything about it all at once.
So if we can't know exactly where an electron is, how do we describe it? Well, we use a set of 4 quantum numbers that act like a probability address. Think of it like this. The first number, the energy level, is like the city. It tells you the electron's general neighborhood and energy. The next 2 numbers describe the orbital shape and orientation. That's like the street and house number, defining the shape and direction of the probability cloud it's most likely in. And finally, the spin tells us a basic property of the electron itself, whether it's spinning up or down. Together, they don't give you a dot on a map, but they give you a complete description of that electron's home inside the atom.
Okay, I know. This journey from solid balls to fuzzy clouds of probability might seem pretty abstract. So why does any of this actually matter in our everyday lives? Well, it matters because everything is made of atoms. Understanding how they're built, especially how those electrons on the outside behave, is the absolute key to manipulating our world. It's how we understand chemical bonds, how we predict reactions, how we engineer new materials, and how we build pretty much all of our modern technology. This fundamental knowledge has powered incredible progress. Our ability to mess with atomic bonds gave us everything from lightweight aluminum to advanced composites, and understanding how atoms interact with energy is the basis for medical tools like MRIs, and it powers the tech in our pockets, from the chips in our phones to the lasers that read our data.
The takeaway here is that every single major technological and medical leap of the last century is built on this understanding of the atom. It isn't just some abstract theory. It is the invisible architecture of our entire modern world. Our journey into the atom really shows that what seems solid and simple is often just the surface of a much deeper and much stranger reality. We went from indivisible dots to probability clouds in just over a century. It just makes you wonder, what fundamental truths are we still completely wrong about today?